Hi, my name is Camille Dunn, and I'm here to present to you on behalf of the Institute for Cochlear Implant Training. Today we're going to focus our presentation on candidacy and outcomes for cochlear implant users with acoustic hearing. My disclosures and financial relationships. And here are our learner objectives. By the end of this presentation, you will be able to understand who a candidate is for electric acoustic stimulation, or EAS. Why would we choose EAS? What are some of the outcomes for EAS? So, topics we'll discuss. We're going to go over candidacy changes over the years. Why does acoustic hearing matter? Why do we even want to try to preserve acoustic hearing? What is EAS, or electric acoustic stimulation? Who's a candidate? Should I use a standard or a hearing preservation electrode? What are some basic programming, which will mainly be covered in the second presentation, where we'll have live coverage of it and we can ask questions at that time. But then we're also going to talk today about bimodal hearing. Why should I bother with continuing my patient use of a contralateral hearing aid? And what are some of the cochlear implant and hearing aid marriages? Meaning some of the cochlear implant companies have relationships with some of the hearing aid companies, which is making it much easier for patients to be able to stream to both of their devices. So first, let's start off with history of candidacy. Believe it or not, in 1985, postlingually deafened adults were first FDA approved for cochlear implants. Patients had to have bilateral profound sensory neural hearing loss and about 0% speech perception. They really got nothing. Finally, in 1990, the FDA lowered the age for implantation to 2 years. That was further lowered to 18 months in 1998. In 2000, it was lowered to 12 months, and finally, recently, in 2020, it was lowered to 9 months of age. As of 2012, I always think this is such an interesting statistic. Gallaudet University Elementary had 50% of its peak enrollment, and this is per an NPR audio that I listened to. What does that mean? Why is that important? Well, Gallaudet University is primarily for deaf education, and if they had 50% of their peak enrollment, that means maybe more people or more hearing impaired elementary school age children were being enrolled or mainstreamed into regular schools. Primarily, this is because they were receiving cochlear implants, and cochlear implants help to maintain or mainstream these children into normal hearing schools. In 2014, the FDA approved the first hearing preservation electrode for adults with expanded criteria. This was huge. For a long time, there was kind of a gray period between where patients would benefit with a hearing aid and where patients wouldn't benefit from a hearing aid. But the problem is some patients still had pretty good low frequency hearing, even though in the high pitches, the hearing aids weren't really helping them at all. And so this was huge because this was the first time we were able to, the FDA approved a device where we could stimulate the high frequencies with a cochlear implant, but provide low pitch hearing in the lower frequencies where patients had better hearing using a hearing aid. And so this really expanded the criteria. It opened up the number of patients that would benefit from cochlear implants, and they didn't have to wait until their low pitches dropped out in order for them to be able to take advantage of cochlear implantation. Finally, in 2016, Medel then received FDA approval for a hearing preservation electrode. So what does expanded criteria means? It means that we had implantable solutions for patients with significant residual hearing. They were able to utilize ES or acoustic electric stimulation in the same ear. And furthermore, as a result of this, because we were implanting patients with more residual hearing on the implant ear, typically we're implanting the poorer ear. And so what that means is the contralateral ear, or the ear we weren't going to implant, was even better. And so a lot of those patients were still able to take advantage of continuing to use a hearing aid on that ear. So when we have somebody who has a cochlear implant on one ear and a hearing aid on the other ear, we call that bimodal hearing. So we're going to start off and talk about the electrical acoustic stimulation. What is EAS? Well, combining acoustic and electric hearing on the same ear. So if we have this person here, what they're doing is they have acoustic hearing and hearing with the cochlear implant. So they're getting electric and acoustic stimulation in that same ear. Typically, we do this in one ear. Now we have some patients that have bilateral EAS, but when this transitioned, or when the FDA first approved it, it was only approved, and the indications may still say only one ear, but we can do off-label and implant patients with contralateral EAS hearing. The typical scenario is, though, we want to start with one ear, see how that patient does, combining the acoustic and electric information. And in this case, patients typically wear a contralateral hearing aid. Now we can accomplish acoustic and electric hearing a couple different ways. There are some FDA-approved hearing preservation electrodes. These are electrodes that are shorter in length than a traditional standard electrode that I think most of us are used to working with. And the hearing preservation electrode is indicated by the FDA as being a hearing preservation electrode. So what that means is the cochlear implant company had to go to the FDA, present to them data that showed the hearing preservation outcomes under their clinical trial with that particular device. And then the FDA would approve it and say, yes, we consider this FDA approved for hearing preservation. Just a note of how long this process can take. We worked with one of the companies on getting FDA approval for a hearing preservation electrode from the year 2000, and it was finally approved, the L24, in 2014. So it is not a short process. Along with that process, there are oftentimes different iterations of the hearing preservation electrode. For example, it started out being a 6 millimeter, six channel electrode, but that first trial, the patients perceived really high pitch signal or stimulation, and it didn't sound natural to these patients. It was really super high pitched. And so we knew that was probably an electrode that wasn't long enough. So that electrode was then changed to a 10 millimeter electrode with 10 millimeter electrode with 6 electrode channels. That was further revised again to be a 10 millimeter with 10 electrode channels. And then finally, the L24, which is 16 millimeters with 22 channels, was what the FDA ended up approving. So that FDA clearance is a long process, and it takes a long time. You have to present a lot of data, and if it is pretty clear cut, the FDA will approve it. But certainly we know hearing preservation is not something that we want to take lightly, especially if patients are being implanted with pretty significant amounts of residual hearing. The other option for accomplishing EAS type hearing is using a standard length electrode. And contrary to what we thought when some of these hearing preservation electrodes were first FDA approved, the standard length electrode is probably the most commonly used electrode for hearing preservation. These electrodes do not have the indication for hearing preservation, But because of the way they're made, they're flexible, maybe they're thinner. We have some new technologies that we're using along with implantation to hopefully try to preserve residual hearing. And why it's become more common is people were reluctant to put a shorter electrode in if a patient lost their residual hearing. At the University of Iowa, the outcomes that we have with the shorter electrode are certainly better than that we have with a standard length electrode. But there is a concern. What if they lose their residual hearing? Do they have to have that electrode taken out and put back in? And we'll talk a little bit about that as we move on. Some other words that you might hear when we talk about EAS, you might hear it called hybrid. You might hear it called A+E. You might hear it talked about as a short electrode, hearing preservation electrode. All those things, really tie back to what we're trying to accomplish in the end. We want these patients to be able to take advantage of acoustic and electric hearing in the same ear. So these hearing preservation electrodes, I talked a little bit about the L24. The L24 from the electrode contact here to the electrode tip is 15 millimeters, but if we take it from this part here to the end, it's 16. So it is 22 electrodes, but 4 electrodes on the most basal end of the electrode are often disabled. This is because these 4 electrodes are going to be just right over or right around the round window, and it's going to be part of the ear that is not going to be stimulable. There aren't nerve particles there that we can stimulate. So what we do is we turn those 4 off and use the other 18 electrodes. MED-EL also has hearing preservation electrodes. They have the Flex 24, and if you look from electrode contact here to the tip, that's about 20 millimeters in length, so it's a little bit longer than our Flex 24, or than our hybrid L24. It has 12 electrode contacts. They also have a Flex 20, which is very comparable to the hybrid L24. It's 16 millimeters in length and has 12 electrode contacts. So let's talk a little bit more about standard length versus hearing preservation electrodes. It really is physician-clinician preference. Overall, shorter might preserve better because it's going into the cochlea a shorter distance, and we're staying away from that apical low-frequency hearing that we want to try to preserve. But the standard electrode is longer, and that allows the patient a longer electrode if they would lose their residual hearing. Luckily, all 3 companies that are currently FDA approved in the United States, MED-EL, Cochlear, and Advanced Bionics, have standard electrodes that we have tried to use to try to preserve residual hearing. And if that's accomplished, all 3 companies do offer external processors with ipsilateral combined processing capabilities. So we're able to use acoustic and electric stimulation in the same ear through the same processor. And those processors with the combined stimulation can be used with either the standard or the hearing preservation electrode. So what about the benefits? Why do I care? Why do I want to preserve low frequency hearing? Well, low frequency acoustic hearing provides the user with timing information or fine structure information. And that is really, really important if you want to listen in backgrounds of noise. Most of our patients come to our clinics because they can't hear when they're in a large group, an environment with background noise, and so they're coming to us because they can't hear in backgrounds of noise. And one of the benefits of preserving that low frequency hearing is the low pitches provide timing information. So if we look at cochlear implants, they typically provide envelope information. So if we have an original waveform that looks like this, you're going to see that this envelope mimics this part of the electrode. So it mimics that. It provides the envelope information of that speech sound, which is very helpful. But what the acoustic low frequency information does is it provides this timing or this up and down information that you get from the original waveform. So combining those two types of technology really provides a wholesome sound to that patient. They get the low frequency timing information to help them pull sounds out of background noise, and then they get the envelope information, which supplements that timing information to provide that whole signal. So other benefits that we talk about a lot with A+E or EAS type hearing, patients have improved quality of sound versus the traditional cochlear implant. They have improved speech perception abilities. We've been able to show that over and over again with lots and lots of different research. They have better frequency selectivity, which helps understanding in those backgrounds of noise. And that is all due to that low frequency timing information. Also, music. Music has timing information. And so by providing electric acoustic stimulation, patients are able to appreciate music a lot better. They can use that envelope information to try to help understand the lyrics, but the low pitch information really gives them the timing information that they need when wanting to hear music. The other thing that those low pitches help is they maintain localization abilities. So most of the time, patients are going to have similar or pretty symmetrical low pitch hearing between the two ears, and that they'll use that low pitch information for localization abilities. And when we have different types of high pitch information, so the hearing aid on the contralateral ear really can't provide a lot of high pitch information, but the cochlear implant on the implanted ear is. And so there's a mismatch between the type of information that is provided between the two ears. And we need similar information to be able to localize. Low pitch information is provided for localization through that timing. And so we use our ITDs or interaural timing differences. Did the sound arrive at my hearing aid ear quicker than it arrived at my implanted ear? Or we use level information for the high pitches. And unfortunately, when we have a mismatch in the high pitches, was it louder in my implant ear than it was in my hearing aid ear? Those high pitch information, we're not able to compare the ILD information between the two ears. And that's why even bimodal users who don't have acoustic hearing on the implanted ear don't have very good localization abilities, even though they have hearing being provided to both of their ears. There's no like information between the two ears for the ear to be able to compare ILD or ITD information. So by maintaining that low pitch information, we're able to still maintain that localization abilities. So we have also been able to show benefits of acoustic electric hearing through high density EEG. And this is some information here. You can see in this schematic on this side, this is before cochlear implantation. The frontal language area here, you can see there's not a lot of stimulation going on. And the primary and secondary auditory cortex, likewise, there isn't a lot of information going on. But when we look 6 months after cochlear implantation, with EAS, we're able to see those critical auditory and language areas in the brains being activated. And this activation is very comparable to the activation that normal hearing listeners are able to get. When we look at this compared to patients who don't have EAS, they get activation in these language areas, but it's often delayed compared to that of EAS or normal hearing listeners. So it's going to take them longer, or it takes them longer to be able to process the sound. And most of the time we're listening to connected speech. And so we need that timing information. Again, it goes back to being provided with that low frequency timing information, which helps us when we're trying to process language and auditory information. So what are the EAS systems? Let's talk about it. As I mentioned before, Cochlear, MED-EL, and Advanced Bionics all have external processors which provide acoustic and electric stimulation using the same processor. And there's different ways that we can program that information. They are all built into EAS type systems, which now the new Advanced Bionics software has NOAA built into their Target CI programming software. Some of the other systems all have electric acoustic portions built into their programming. But the big thing that we need to remember is regardless of how we program the device, we still need to verify it. And verifying the acoustic portion of the EAS system is done traditionally. It's done using real ear measurements. Even though our software is telling us that we're meeting targets, we want to verify those targets with an EAS or real ear type system. How it works is acoustic information is amplified. That low frequency information is sent through the normal pathway. And at the same time, the sound processor is converting high frequency signal or the high pitch information that they don't have acoustically to a digital signal, and it sends it through the cochlear implant. The implant, as you know, bypasses the damaged inner ear and sends sound directly to the hearing nerve. And then both of that information is combined in the brain. So the brain is taking the acoustic and the electric information and putting it together to make one sound percept.